Hello everyone. This is our final approximation method for exam 4. It's called, well, I've heard Runge Kutta, Runge Kutta, um, different pronunciations. But the idea is that it's going to use, if you recall, an improved Euler's method, the last lesson, we used the average of two slopes to get an approximation. Here, this method uses four slopes, and there are actually other models that use more than four slopes, so commonly referred to as RK4, RK6, and so on. Sketching this and the formal proof are very cumbersome, so for sake of time, I'm going to omit them this time, unfortunately, but if you're interested, I'd be more than happy to supply you with the proofs and a reference for a sketch. But the theory behind the formula is, after using the fundamental theorem of calculus and Simpson's rule, so that's way back from calculus 1, we get the following approximation for our solution, y sub n plus 1. And so it's y sub n plus h over 6, that 6 is coming from Simpson's rule. And then the y primes represent the derivatives, evaluated at each of these different x values. And so the first slope, so y prime is the slope, the derivative, of course, and h is the step size. The first slope that we define is just the Euler method slope at the initial point, x sub n, and that we call k1. Then the second slope is, again, the Euler method slope, but it's at the midpoint between x sub n and x sub n plus 1. So if, let's say, this is 0 and this is 0.2, the midpoint would be 0.1, okay? And that's the x sub n plus 1 half h is going to give you that value, depending on your step size, of course. And there, my example was 0.2 as a step size. So then here's our new y value, and we continue to get, and we call that k2, then we continue to get what we call k3. It's the improved Euler method, and then k4 is the Euler method at the step that we took, the x value of the step that we took. So if we substitute all that in terms of the k's, this is our formula, and here's the formal statement of the method. So we're approximating dy dx as f of xy, and here's our initial condition, step size of h. So ultimately, this is sometimes what's referred to as the Euler form. Ultimately, our approximation is the original previous y value and then plus hk, but this is where k is all of this, the 1/6 times the combination of those slopes. And then here it's simplified for us to list k1, 2, 3, and 4 in a nice convenient fashion. So the first thing, as always, that I ask you to do on this exam is to solve by a method of that we previously used and verify the exact solution. So here's the initial value problem, here's the initial condition, and here's our exact solution. So we want to verify that by the method of undetermined coefficients. So we start with the given y prime equaling x minus y plus 2. Okay, so this is a non-homogeneous first order linear differential equation. We could solve it by many methods, but I'm just choosing the undetermined coefficient method. So what we'll do is we'll bring all the derivatives in the function y to one side. So y prime plus y would be x plus 2. From there, we can get the characteristic equation. Actually, I'm sorry, that's a non-homogeneous, so before the characteristic equation, the associated homogeneous, and that would be just setting it to 0, of course. Okay, now the characteristic equation. So r plus 1 is 0, r is -1. So then our complementary function, or the solution to the non-homogeneous, is y sub c equaling c1e to the -x. Okay, but this is non-homogeneous, so the solution is composed, because it's a non-homogeneous, recall that the solution is composed of the complementary plus the particular. And now we have to use undetermined coefficients to get the particular solution. So our guess is based on the function, and it's x plus 2, so we'll say that y sub p is ax plus b. Remember, we're going to compare that guess to the complementary function to see if there's any duplications, and we can see that there are no duplications, so therefore that's a good guess. Excuse me. We'll have to take a derivative because we're going to find a and b by substituting into our differential equation. So y sub b prime is a. Okay, then our substitution, I'll rewrite it, y prime plus y equals x plus 2. And we have y prime, ax plus b, plus y, a, equaling x plus 2. If we compare the x's, we get ax equals x. So dividing out the x's, a is 1. Compare the reals, or the constants. Get b plus a is 2. We know a is 1, so b plus 1 is 2. So b is 1 as well. So therefore, our particular solution, y sub p, is ax, or just 1x, plus b, or just plus 1. Okay, so now I'll come over here, because our actual solution is y equaling y sub c plus y sub p. Actually, I'm not going to write that out again, I'll just make the substitutions. So c1 e to the -x, and then plus x plus 1. And now we use the initial conditions to solve for c1. And the initial condition was y of 0 is 4. So then we have that 4 is equal to c1 plus 0 plus 1. So c1 is 3. And then finally we could write our exact solution, 3e to the -x plus x plus 1. So you can see that's what we had set out to prove. Okay, so now the method. So Runge, Kutta. What I did was, and this is in the notes, I made it so that it would be a little bit less cumbersome to go through this by just writing the numbers out, and I typed them into a document. So we'll just follow along. Here's the page with the solution, but I'm sliding in the previous notes so that we could focus on the formula. So the formula, once again, is ultimately y sub n plus 1 is y sub n plus hk, but we need k. K is this combination of the slopes, and here's all the individual slopes listed. So y sub 1 is going to be y sub 0 plus hk. And I listed, there's k again. Here's the function, and this is the initial condition, which basically means that x sub 0 is 0 and y sub 0 is 4. So our first step, if you read the directions here carefully, says 0 to 0.5 with the step size of 0.25. So our first step is going to be 0.25 for our first x value. K1 is the function. Okay, so this is the function, the y prime, evaluated at x sub n and y sub n. Now what I like to do is I like to actually show the calculations and substitutions of those respective x and y coordinates before plugging into the function. You could do whatever is convenient for you, but I think this is a nice way to proceed. So it would be f of 0, 4, because the initial x value is 0 and the initial y value, y sub n, is 4. So that's the previous, the x sub 0, y sub 0 values. And so we plug in x is 0, y is 4, so 0 minus 4 plus 2 is part of the formula, so we get negative 2 for k1. Okay, the next slope, k2, is f of x sub n plus 1/2 h. X sub n again is the previous x value, so that's the 0, and then which is the step size of 0.25 that's given. Okay, this comma is separating the x coordinate here from the y coordinate, and the y coordinate is y sub n plus 1/2 h k1. Actually, I guess we don't even need to reference these formulas that much anymore, because the way I've written up the solution, they're right there. So we're at the point here now where we had, here's your original y sub 0, y sub n, 1/2 h 0.25, and then the k1, that's the previous k that we just found. So that's the k1, negative 2. And so just crunching those down, that would be the function 0 plus 1/2 times 0.25 is 0.125. Crunching this little portion down for the y value, we get 3.75. And then we're going back to, this is our main formula, x minus y plus 2. So for 0.125, 3.75, x 0.125, y minus y 3.75, and then plus the 2 is part of the formula, and there's the value that we get. Now for K3, it's x sub n plus 1/2 h again, so that's the same as the previous value, but I showed the substitution literally. The y value changes slightly. It's almost the same, except it's got K2 instead of K1. So now this K2 value is what goes there. Okay? And there's the 1/2 h again. So then we crunch down the numbers. 0.125, the same as the previous x. Y changes a little bit because the K changed. And then into the formula, here's our x minus our y plus our 2, again, the formula. Crunch that down. And now finally for K4, we have x sub n plus 1, so now this is the x sub n plus 1 value, the 0.25, because that's our step. And the hk is the h of 0.25 times the k that was that previous k value, k3. And so there's our x, crunch down our y into the formula, x minus y plus 2, and that's what we get. So now the average, or well, it's not really the average, but it's a combination of these slopes, in a sense an average. So just plug into the value for k, the overall slope, and then this is the formula, 1/6 k1 plus 2 k2 plus 2 k3 plus k4. So 1/6, there's k1, 2 k2, 3 plus 2 k3, and then plus just k4. Crunch all that down, and this is what we get. And then ultimately y1 is y sub 0 plus hk. Y sub 0 was the 4, that was our initial condition up here. And then plus the step size 0.25 times the ultimate k value that we just found and this is the value that we get. So then the next step, and we're going to verify how close that is momentarily by getting the exact value. So then basically we just do it over again. But now y2 is y1, the previous y value, plus h times k, where k is the same, and the function obviously the same as well. So x2 now is 0.5, so we took another step. k1 is the previous x value, x sub n, which is the 0.25, so that's the x sub 1, and then times y sub n, which is the previous y value, y sub 1. So this is x sub 1, y sub 1 if you like. And then again we go to our formula. There's the x minus y plus 2. That's the formula from the top, of course, I was pointing to. And so then crunch that down, repeat the process as from above. X sub n plus 1/2 h, the midpoint is 0.25 plus 1/2 times the step size, 0.25. The y value is going to be the y sub n value. Okay, so this 3.586, etc., is that value, and then plus 1/2 times k and times the previous k1. Okay, so then there's the functional values, and we'll plug them in. X minus y plus 2 again, crunch it down, go to k3, same x value, 0.25 plus half of h, which ultimately was 0.375, but now the y sub n, or the y value, is the y sub n, so again, back to this 3.5864, etc., but then 1/2 0.25 times the previous k value, k2. And crunch those down, those are the coordinates, plug them into the function, x minus y plus 2 again, that's what we get. And then we go to k4, and that's x sub n plus 1 now, so that's the new step, 0.25, or excuse me, 0.5, and then the y sub n plus hk3, still back to that original y sub 1 value, 3.5864, etc., and then plus h.25 times k3, which was that previous k value. And then we crunch those down, there's the coordinates, and then here's our famous x minus y plus 2, the original equation. So there's the number we get, and then we just substitute all the k values into the ultimate k, 1/6 of that sum, and you could check the substitutions. Obviously you're checking my calculations as well. And then finally y2 would be y1, so back to that 3.5864 again, and then plus 0.25 times this ultimate k value, and that gives us this number here. So these are the two approximate solutions. And if you wanted to build a little table of the approximate and the exact, for the exact, again, we'd have our x values here of 0.25 and 0.50. The exact or actual, whatever you want to call it, remember that always uses the solution. And if we look back at the solution, it was 3e to the negative x plus x plus 1. And so for for our approximations, 0.25 was the 3.586426. I'll go to 6 decimal places. And for 0.5 is 3.319 629 again to 6 decimal places. And if we do the exact, let's say for x equal 0.25, it's just building a 0.25 in here for x, so 3e to the negative 0.25 plus 0.25 plus 1. Let's put dot 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 at that point. And the exact solution for that is 3.586402. So you can see it's really close right away with even a bigger step size than the improved Euler. We got a much, much better approximation right away. And then the exact for this 0.5 value, again just plug in a 0.5 instead of a 0.25, you get 3.319592. And again, a really good approximation, and we didn't, the cumulative error didn't really increase dramatically. Okay, so that's the end of exam 4. Read the announcements in Blackboard, the exams posted, and read the announcements for the due dates and such. And so we have one more unit to study, and we're going to call it exam 5, but it's really what your final exam is going to be. So there's, on the final exam, there's no new material, or no old material. It's all what we're going to see starting with our next unit for exam 5, what you can call exam 5 or the final exam. So we'll see you when you're ready.